screen here. This this particular webinar is based on a presentation of how we, well, the presentation is based on how we calculate fields around an antenna in IXUS, and in particular, you know, new antennas that's used for 5G analysis. I've through quite a few discussions with clients and prospects, and you know, and people that show interest in IXUS, it came to my attention that people want to know what really goes on in the engine of our tool, specifically our field calculation engine, and what approaches do we follow, and that is what I would like to share with you today. Okay, but before I do that, a bit of background about, you know, what sort of drives us to continue to look at ways in which to provide faster simulations is, you know, if we look at just the tempo at which mobile communication is increasing in the world, we're standing here at about 8 billion people. You know, I don't know how accurate this figure is, but it sort of illustrates the point in the sense that, you know, there's quite a lot of people in the world already using some form of a mobile handset. You know, and this trend, especially in countries like, for example, the US, this trend is just increasing almost exponentially. You know, as the operators are endorsing and rolling out 5G antennas and radios, these to support this this growing market, the numbers are increasing, and that also fuels various industries, and we are one of those industries. You know, IXUS is a RF safety analysis suite, and we want to make sure that, you know, we stay ahead of the curve in terms of our simulation capabilities. Yeah, so this is just a bit more in the you know, a bit more graphs to illustrate this point. You know, it's assumed that, well, it's expected that the adoption with 5G is going to hit, you know, almost 1 billion mark in 2022. I don't know if that prospect is still accurate. This was from an Ericsson mobility report last year, but regardless, you can see the growth from where we're standing now to what is projected in the next 5 years. That the numbers are going to more than double. You know, so if you stand back a little bit and you think about what features of these 5G antennas of these 5G systems are attractive to users, you start becoming a little bit more, you know, it gives a bit more insight regarding the, you know, the type of technology that we will have to cater for in our simulation packages. You know, and what's really fueling this adoption is the fact that these antennas support faster and download and upload speeds. And one thing that is in particular is that, you know, more than one devices can obviously be connected at once to a 5G station. And this station has got a lot of intelligence in terms of dynamically adjusting its properties in order to service this, this dynamically changing user environment around it. So that is something that I will also focus on a bit later, because it tells us a little bit about how these antennas work. And then it also then highlights a few things that we need to take into account when modeling these antennas in IXUS. So that's just the technology, you know. In terms of, as you can see here from the figures, the users are just increasing everywhere. So, you know, the densification of these antenna systems in the environment is also something that's very important to note, is that these antennas are being deployed on quite rapidly. In particular, something that I noted when I visited the US now at ConnectX was just the increase in popularity of micro or small cells for the deployment of some of these antennas. That is really something that I noted regarding the rollout here. Okay, so as I mentioned, the the deployments are really everywhere. So we don't just think of conventional tower systems now. These antennas are placed on complex rooftop environments. use a combination of fixed beam LTE type of antennas, maybe with a few C-band antennas. I don't know my antennas so well from pictures, but yeah, it's a complex environment. There's strand mounts, which I'm sure a lot of people in the audience are familiar with. Is the antennas here mounted on these utility lines, and then obviously there's the pole-mounted options that you see in this figure over there, over here. This is just outdoor antennas. Also in the indoor scenes, you see these systems being deployed being deployed everywhere. Here, for example, is a nice Ericsson radio sitting inside. There's antennas. These obviously is not 5G antennas, but they're sitting here on the rooftops, on the ceilings of these buildings. So what I hope to drive home with this point is the fact that the systems are being deployed, and it really is our job in IXUS, when you model these environments in our tool, to make sure that when you plug in an antenna model, that what you get is something that depicts the behavior of that system as accurately as possible. Here is an example where I just take one of these environments. It's a rooftop where we have a 4G antenna deployed with a 5G system, where we've just modeled this roof environment and then calculated the fields on this environmental slice that we call it. It's in the IXUS standard, but obviously we support also other standards like FCC and so on. So the focus now of the talk is going to shift a little bit to go into what the math is. I'm not going to show you too many formulas, but I want to step back and look at a few simulation approaches that we used to model these 5G antennas. And I hope it's sort of, the progression of introducing those methodologies sort of motivates why we settled on the technique that we are using. And also, why we settled on the technique that we are using at the moment. So before we can do that, I just want to emphasize, a few differences between 5G and 4G systems. So over here you see is a fixed beam LTE panel, 4G system, conventional. You see the beams pointed electrically to a particular point in space. And on the right, we have a 5G zone. Now, obviously, I'm not comparing apples to apples. These antennas are different. They're not driven with the same power. This is just to produce something that I can show to you to illustrate some of the property difference between the properties. So first thing that you notice that the 5G zone could be more, is a little bit larger in terms of vertical and azimuth extent. And so what we should take note of is that the 5G antenna have a beam that is steered to a particular handset or mobile user, and this beam what makes these systems so clever and is that beam can be adapted dynamically in what we call dynamic beamforming to service the particular point that requires it, where the traffic is located. And this is as opposed to fixed electrical tilt LTE systems or 4G antennas. So this is what we need to account for, the fact that we've got a beam and that beam can be steered anywhere in space. Not just that, we also, the systems can also form multiple of these traffic beams. Obviously, then power will be reduced. And I will show you a little bit later in IXUS in the slides, how a user can accommodate for that factor. Okay, so now what I'm going to do is I'm going to go through a few iterations, simulation approaches that that can be followed, all of which can be done in IXUS. This is now in the engine, right under the hood, as you might say, that goes into providing an antenna model. So this is the approaches and some drawbacks, and then and why we eventually selected the technique that we did. Okay, so the first technique, if you have an antenna system, it's got certain parameters. then you can obviously revert to using a full wave computational electromagnetic tool. I am biased towards FECO, which is a world-class computational tool. We've got a FECO model here on the left-hand side. That is a pretty, it's not a detailed model, but it's a representation of what an antenna array might consist of inside one of these 5G systems. It's got a number of elements. These are cross dipoles, and those dipole or those antenna elements here, that's positioned in front of a reflecting surface, can generate for us this very narrow traffic beam. And we can match its properties from information that we get from the manufacturer. What we can then do also is we can dynamically adjust that beam, or as we say, electrically scan it to the extent of where this 5G antenna will support that behavior. So we phase this element electrically, and then we can steer the beam outwards to the extent of what the 5G antenna supports. So here the beam, I think, is steered to about 60 degrees. And what is also, good to note here is that by doing so, you also account a little bit for the physics of what the antenna will do in terms of the gain that will sort of taper more towards the edges of that scan range. We expect that. But what's the drawback? And and if you concatenate all these multiple scanning positions, in a sufficiently fine scan sort of grid, then you can concatenate that, and you can create something that looks like this on the right-hand side, which then depicts the 5G antennas radiation properties, where the beam was phased to all the positions where it's where it's supported. The problem, however, with this approach that we found is that it's very costly to simulate each and every potential beam position, and because you need to run multiple computational full wave computational analysis, typically based on something like the mether moments, and that that can become a hampering factor. Okay, so what's a faster approach? So for option B, faster approach is you only model one of the beams. So you only model one of these beams, and then you mechanically rotate the antenna system. So you would mechanically rotate the system in space to account for the various positions that beam can be radiated at. But if you recall in the previous slide, I noted that unfortunately, you will not really see the effect, the electrical effect of the beam that tapers off towards the edges of the array. Like you will see here on the left-hand side, we have our mechanical tilted model, and on the right-hand side, we have our electrically steered full wave model. So you do see quite a significant difference here in the edges, and that is something when it comes to simulations and modeling that we really try and get as accurate as possible from our side, because we know that if you deploy these systems on a roof or whatever, that can have an effect. Okay, so one is very costly model, the other one's not accurate enough. So what are we going to do? So this is the third option, option C, which is also the one that we adopt in IXUS, is we go back to how we model. If we have an antenna and we have radiation properties, that could be, well, the radiation properties we know is typically the field patterns. If we have the horizontal and vertical field patterns, that is very readily, in most cases, readily available from manufacturers. If we have that, then we can actually represent that antenna as a linear array of point sources. And then what we do is we summate the fields that is emitted from those point sources in an approach that we call synthetic ray tracing. And that this approach is documented in this standard over here, the IC standard. So we use those rays to calculate the field at any point near the antenna, even in the near field, you can do that. So I promise that I won't show too many formulas, but here's one that's important. So this is what I mean with saying that we combine these rays. So what we do is we take an antenna. We don't know what's going on inside. We only know its fields, its radiation properties. We build up an element pattern, and then we apply that element pattern to various number of point sources in that radar. We don't know how many, and we don't know the spacing, but I'll get to that in a minute. And then by doing that, we can calculate by choosing a appropriate function for this element pattern. We can calculate the electric field at any point, and then from the electric field, we can go back and calculate power spectral density. And then if we have that, obviously, then we can calculate. We can use the limits of the particular standard, like FCC or ICNIR, to relate it to the what we call the exclusion zones, or the regions where that is unsafe to be in. Okay, so the question is, this is a nice verified approach in a well-known standard, but what should you choose if you want to use it for 5G analysis? What should we use for our element pattern? So we already know that we can get some data from the manufacturers, and the pattern that we request for this particular modeling is what we call the traffic envelope pattern from a manufacturer. Now, if you look closely, you will see the green pattern over here, which is the pattern supplied by the manufacturer. The solid line is the vertical pattern, and you will see you can definitely make out some distinct lobes. That means that is where this traffic beam has been steered towards during this measurement phase of the particular model by the manufacturer. So they have this data available, and we ask for this data. So what we do is we use the horizontal and the vertical traffic envelope pattern, and then we do an interpolation to form a three-dimensional element pattern, the one that we see over here. And we can use that now in our ray tracing approach. So what we do in our ray tracing approach is we apply this element pattern, which is based off of the traffic pattern from the manufacturer for this 5G antenna. We apply this element pattern to an arbitrary number of point sources, collinear array point sources, to represent this 5G antenna. So as most of you are probably asking at this point in time, how do you know how many elements? How do you know what the spacing is? And how do you know what the complex, the complex phasing is, electrical phasing, or the gain scaling, amplitude of each of these elements? So that really, to answer that question, or I'm going to answer that question by saying, that is really the key step of the antenna modeling that we undergo in our company, where we synthesize the correct behavior that the antenna manufacturers supply us. So what we do is we use an intelligent optimization approach to calculate the number of elements and the spacing and the scaling of each one, so that the patterns that we generate using our ray tracing approach matches the patterns that the manufacturers provided. And this is the black lines over here. So so this is what we try to, what our antenna engineers do to make sure that the model accurately matches the data that's provided by the manufacturer. It's also worth noting that, in the end, before the model is finalized, the gain of the total model is also, is also scaled so that it's in alignment with the traffic envelope beam max gain. So by doing that, you generate a 3D exclusion zone, or a model that's capable of simulating a three-dimensional exclusion zone that can accommodate for any position of where the traffic beam might be situated. And here is just a comparison between the full wave electromagnetic model. So let's say the reference result and the approach in IXUS, which uses ray tracing. So as you can see, there's really excellent agreement, and we verified this quite rigorously in the past. Okay, but at this point, you might also think that, well, if you scale everything according to the gain of the traffic beam, you might sit with a pretty big exclusion zone that's statistically very unlikely, or it is unlikely to occur, that this antenna will sit, all the beams will be at full power all the time. As I showed in a previous slide, they do reduce as the load increases. So what in IXUS, it is more than possible by adjusting the input power to account for this, either duty cycle or power reduction factors or so on, to scale the total power. And these are just two images where I emphasize this point. One, I have a 4G and a 5G antenna in combination. So you'll see here that we have a pretty large exclusion zone. Nothing is scaled according to power reduction factors, but on the right, we've applied, I'm not sure exactly what we've applied as a setting, maybe 25%, and the exclusion zone is then scaled accordingly. So those particular settings we don't supply or prescribe. The settings should be obtained on the user side. One question that I also received is, how do you guys know that? How do you verify this ray tracing methodology? So this is one example of how this is done in the IEC standard. You have this full wave reference model. This is a panel antenna, and then you have 3 set dimensions, so you can create it in any computational electromagnetic tool. And then they also provide reference results for it, which is effectively the near field that's sampled on a line in front of the antenna along its bore side. And then on the right here, I just plotted those results for you. The blue line is what we obtained from the full wave EM tool, and the orange line is what IXUS produces. So these results comes out of our validation reports that we do every time we make an adjustment to our calculation engine. Okay, so to conclude, I think this audience is very well aware of the fact that 5G antennas are rolling out everywhere, and they are also being deployed quite rapidly. So one needs to be sure that your analysis is based on antenna models that's sound when it comes to calculations. And we take pride in making sure we offer that. And we do that by what we found is the very efficient use of our ray tracing methodology in combination with the traffic envelope patterns that manufacturers provide to build a model that can be used for these simulations quite nicely. Thank you. That was what I wanted to share with you. I hope it gives you a bit more insight into what goes on in the engine of the calculator and how we model things. And also, when you request antennas from IXUS, why we do place emphasis on verification on our side, making sure that what we deliver is correct and corresponds to the actual working of the antenna as best possible. Okay, I am going to, let's see if we've got a few questions. So you guys are